Everybody, lovely to see familiar names. John Kay, I see you again. Liz, friends coming in from Portugal and various other corners of the world. We're going to talk today about really the two main software offerings that RBR has. And I'm going to, I didn't set up a Zoom poll, but I did want a quick show of hands and just drop a line into the chat. Are you more interested in hearing about Ruskin or RSKtools? If you have a particular preference, now is your chance. There's actually quite a lot of material, particularly on RSKtools, that I could give. I do tend to go through it fairly quickly, but I'm happy to either concentrate on that part or the Ruskin part. I'm going to start and just do it as I'm planning on doing it. But if you leave a comment, I'll look at them in about a minute's time and see whether you're interested in me zipping through Ruskin and getting straight to RSKtools or vice versa, or maybe you don't know anything about either of them, and that's just fine as well. What is the division between the two? Well, Ruskin is the only piece of software that you need to control every RBR instrument. And so from deployment to download to display, it's your one-stop shop. We can also simulate any instrument that we make so that even if you don't have hardware, maybe it's on its way to you, or maybe you're just evaluating whether you're interested in RBR, you can use Ruskin to look at the capabilities and see what it would be like to use an RBR instrument. Also to be able to assess using the autonomy engine, how long your deployment could last with RBR. We spend a lot of time on very, very low power electronics to enable your deployments to last a long time, but sometimes your deployment conditions can affect that, or even the choice of batteries you use, and Ruskin will help you simulate all that. RSKtools is designed, it is a MATLAB toolbox designed to read the files that are downloaded from your instrument. So Ruskin will download the instrument and produce an RSK file on disk. RSKtools is a MATLAB toolbox that allows you to do the post-processing easily. It's also a good example of how to do post-processing on our RSK files in any language, not just MATLAB. We do have an alpha version of RSKtools in Python, which is available, and you might be using another language like Julia or R or any number of things. And the MATLAB toolbox serves as really the prime example of the structure of code that's necessary to read those tables. I'll talk a bit more about that in a second. So I'm going to have a quick look at my chat window just to see if there are any votes for both Ruskin, RSKtools, Ruskin, okay, so we have a bit of both. So we'll see. We've got just under an hour, so I'm going to do both, and whichever part I don't give enough shrift to, you can ask me more about it. So we'll start off by talking about Ruskin. It's what we call one app to rule them all. That is to say, it supports every instrument that we built in the last 15 years. It's the only piece of software you need to talk to RBR instruments. We don't make 7 or 8 different packages depending on whether it's a small instrument or a big instrument or the phase of the moon. The software runs, of course, on Macs and Windows machines. We support Windows 10. It runs on older Windows machines, but nowadays we're finding more and more people have actually stopped having a diversity of Windows machines. We also have Ruskin Mobile that runs on iOS, on Apple phones, and Android phones. Today, I'm going to talk mostly about Ruskin Desktop, although I am just making me think. I'm going to turn my phone off so it doesn't interrupt me. Ruskin allows you to do this complete deployment simulation that I mentioned, which is very helpful. And in fact, that's what I'm going to be doing today. I didn't bring a physical instrument to plug in, but I'll show you exactly what you will see because the simulation is very, very close to actually having a real instrument in hand and plugging it in. I'll be showing it today in English, but if you're a Mandarin speaker or French or Spanish or, gosh, I think there's about 5 or 6 different languages that we support, Ruskin runs in your own language. We try to keep those translations up to date and not use Google Translate for them. We have had some comical errors in the past, but those are a thing of the past. Of course, as befitting modern software, it has automatic update. It also contains all the PDF manuals for both what we call the Ruskin user guide, how to use the software, or RUG, and also our hardware guides, which are the RBR instrument guides, or RIGs. And so while those come on the USB sticks and they're available independently on our website, it's quite helpful if you're looking something up just to be able to go into Ruskin and find them there. And we update it about 4 times a year, give or take. So there will be an update coming just before Christmas, I think, and then with some bug fixes, particularly to deal with one egregious one that has turned up in the last 2 weeks. Some of you who are on Macs realize that Apple released a huge new version called version 11 of Mac OS, Big Sur. And Big Sur has some breaking changes for many people's programs, including Ruskin. So when you run Ruskin at the moment, you will get a blank screen. Our engineers are hard at work to fix this. And the version I've got running on my computer today, I'm running on Big Sur and I'm running Ruskin, and it's working great. So we have a fix in the works and it should be out before Christmas. It's a bit frustrating when foundational things change under the covers and you don't have much of a hope of getting Apple to change things on your behalf. So if you want to get a copy of Ruskin, you can find it on the USB stick that comes with every instrument, and you can also find it on our website, either under the products menu and then software, or also under the support menu and software. And you'll find there the links to Ruskin for Macs, Ruskin for PC, the various mobile stores, and also a link for RSKtools for MATLAB that we'll be talking about later. So it's all in the one place. I think at this point, really, I'm just going to jump straight into the live demo rather than giving you screenshots of things. So let me see if I can actually get that to work. Dan, I'm going to ask you to come back. I just want to make sure that my screen sharing is tied to, can you see Ruskin now, or is it still on?
It's still see the PowerPoint.
It's still on the PowerPoint?
Yes.
Okay, then my screen share needs to be stopped and restarted. And maybe if I do this. Okay, how about that?
Yep, now you're in the Ruskin interface. No.
Great, thank you. You'd think after 9 months that Zoom would be habitually trivial, but it appears that I still have some difficulties. So I'm just going to clear up a few things left from my earlier session. You'll be aware, some of you, that we're doing this 3 times a day on Wednesday for different time zones. This is Ruskin. What we have in the left-hand side is what we call the navigator, where lists of instruments and data sets that you have open appear. And the right-hand side is the editor that shows you a little bit more detail of the instrument or data set that you've selected. And in the bottom, we have the chart view. It's a very simple layout and interface. I am going to go into our simulator. So from the instruments menu, I pick simulate, and we immediately get asked which instrument we'd like to do. And these are divided into categories. So we have our compact instruments, which are 25 millimeter, 1 inch in diameter. The standard instruments, which are about 64 millimeters, 2.5 inches in diameter. The quartz-based pressure sensor instruments, our standalone CODA, standalone sensor range called the RBR CODA. And then also you can simulate some of the older instruments that we don't currently have in production, but still, of course, fully support. In the compact instruments, there is really very little to be done to configure them. You can select, say, a solo T, and I'll do that. And Ruskin now builds in its virtual factory a RBR solo. And this appears exactly as if I just plugged it in, except that the 3 letters SIM in front of it indicate that this is not a real instrument. While I'm at it, I'm going to go and simulate another instrument, and I'm going to simulate a profiling CTD. I could add other channels to that CTD, as you see here, but I'm just going to do a fast 32 Hertz capable CTD. So I've got these two instruments now in the navigator, and when I flip between them, the instrument editor on the right-hand side flips as well. With the compact instruments in particular, they're simple to look at, and they're also very simple to operate. We want to hide all the complexity on the inside. So this is a Solo T that's capable of making 2 millidegree temperature measurements. And the first thing we can see is that it's not running at the moment, which is not surprising as it's a virtual instrument. The clock itself is maintained internally, and it can be synchronized either to UTC time or to local time. So you can see that number jumping there to Zulu or back to local when I flip it. I can set a start time for some point in the future, or I can simply say, I'd like the logger to start recording as soon as I say enable in a minute. And immediately it's clear I'm not able to set the end time. That's because we have met very few people who actually want to stop recording. If you go on deployment and your ship is delayed for the recovery in a year's time, you don't want the instrument to stop recording just because you didn't turn up on time. You'd like to gather more data. And so we generally show you when the instrument is expected to stop because of either battery or memory. And so the element to the left-hand side is the one that we expect will be the shortest, will be the limiting factor. So for this instrument, which is currently set up to start now and to run at 2 Hertz, it will run for 150 days. It will record about 25 million samples. And that will take it out until May next year, May the 6th next year. However, if we change the sample rate, let's say we just drop it down to 1 Hertz, you can see that it immediately goes to 540 days, but it's still limited by battery, and that's our little icon of a copper top Duracell battery. If battery was not a concern, you can see that there is an additional 2.7 years of memory available. That really depends on the sampling conditions and the type of instrument you have. And so sometimes these flip so that memory is the constraining factor and not battery. Now, talking about batteries, we use AA batteries on all the instruments. You don't ever need to come back to us for a custom instrument, just in the same way that we use USB-C cables, absolutely standard. The same one that I'm using here to power my MacBook is good to talk to the instrument. And so you don't come back to RBR for proprietary cables nor proprietary battery packs. But you do have a number of choices in battery, and those are the chemistries. So in the AA form factor, the most common battery that we're used to seeing is an alkaline. You see it's third in this slot. The third in this slot is because it's actually not the best power choice available in the AA form factor. Lithium thionyl-chloride batteries, which we ship most instruments with, are made by a limited number of manufacturers. Tadiran, Saft, Gebsi, the green energy battery company in China, are all reputable manufacturers of LTC batteries. And the reason we ship with them is because they provide the best long-term, the highest energy density. And so you get the best deployments out of those. If you were to move to lithium-ion batteries, for instance, which are often branded as Energizer Ultimates, you lose about 50% of your battery capacity. And you'll see that immediately because this estimate has gone from 500 and some days down to 270 odd days. If you switch to alkalines, which are simulating based on kind of Duracell, Rayovac, Energizer, your standard run-of-the-mill manganese-based chemistry, you'll see it falls further. So alkaline batteries only have about 30% of the capacity of a lithium thionyl-chloride. So we recommend lithium thionyl-chlorides whenever possible. The downside, of course, with an LTC battery is the price. They're about $10 per cell, as opposed to an alkaline battery is, in bulk, they're about 10 cents per cell. The other downside with lithiums is that they're hard to transport. It's legal to transport them inside the instrument, but you can't carry spares unless they're in individual blister packs. And that's how, for instance, they arrive here at RBR in the factory, is in individual blister packs. And so they can be a nuisance to transport by air in particular. And so if you're doing deployments that are only lasting a shorter time period, then these other choices are perfectly adequate. And in fact, if you're doing a measurement regime which might be profiling every day, we'd strongly recommend you use one of the two rechargeable options because it avoids things going in the landfill. Nickel metal hydride only have about 25% of the capacity of a lithium thionyl chloride. On the other hand, you can charge them up every night if that's the kind of deployment you're doing, and we don't waste more material than we need to. So you've seen that kind of interplay on this simple instrument between the amount of time we're going to record for and how fast we're recording. And if this was a real instrument, I could hit the enable button and say go. I'm going to flip over to the Concerto, which has a few more features. And let me see now. Oh, look at that. So I may have discovered a Big Sur quirk. There we go. So again, really just a few more widgets on the screen. We've already had the clock and the start, battery chemistry. Now the standard instruments can have external batteries, and so you can indicate any of the Fermato or Fermet battery packs that we have available. Those again, they're not custom battery packs, they're really mechanical pressure vessels that allow you to fill them with AA's again. The Fermatas are filled with D cells, so they have huge capacities. On the right-hand side, we can see the sampling rate goes up to 32 Hertz because it's a much faster and more capable instrument. And you can see that at 32 Hertz, this instrument is limited by the memory. This is a little, rather small icon of a memory chip. And the battery would give you more deployment if you had memory, but you really can't do anything about that. Now, if we change the 32 Hertz back to 1 Hertz, you'll see that the memory no longer is the limiting factor, jumps to the right, and battery is the limiting factor. And if we set this to something that might be more akin to a normal mode application where we're making a sample, I don't know, even every 30 seconds, you'll see that the battery life on RBR instruments is really extraordinary. In fact, we're going to say 10 years because that's really the shelf life of the battery, but the amount of power we're consuming, particularly during the sleep. So we wake up once every 30 seconds to take a measurement, but we then sleep for 29.5 seconds. And our sleep current is about 10 microamps. That is to say, about the same as putting the battery on a shelf and watching it just decay. The other features that are available in the standard instruments are things like twist activation. This is what we call a gating mode. Now, when we say gating is none, we go back to turning the instrument on and off by time. But we can override time and say, we'd like to have the instrument run when you grab the battery end cap and rotate it. And when you do that, the instrument vibrates in your hand. You can feel that no matter how well lit it is, no matter how noisy your ship is. We can't predict what the end time will be as an absolute calendar date because we don't know when you're going to start it, but we can still tell you the deployment lifetime. We have another gating mode, which is the marine wet switch. And the marine wet switch is available on all instruments that have conductivity sensors. It allows the instrument to detect itself when it's hit the water and start recording at that point. In the right-hand side, for battery end caps that have some of the underwater connectors on them, we permit things like real-time streaming data to come out, and so you can enable that for either serial or USB. You can change the serial from RS-232 to 485. You can change the serial rate of the data stream and so on. Enable and disable the Wi-Fi as you go. What you have in the bottom in this chart view is what we call the live plot. The live plot is currently blank because we're looking at a particular instrument and we haven't started asking it for any data yet. I can do that with the little play button here on the right-hand side. Now, in my simulated live plot, we really get garbage data that just kind of cycles around and shows what appears to be random noise. So it's not particularly useful. But when you have the instrument connected to the computer, either over, and it could be over Wi-Fi or USB or serial direct connections, and we do in fact have Ethernet available as well. If you've got an Ethernet dongle, then you could get live readout from some tank, for instance, that you're interested in monitoring. But it might be a very long RS-485 cable that's in the middle of Lake Tahoe, and you'd like to see that live data as well. Ruskin will let you do this, or you can take that data that's coming over that connection and capture it in your own streaming program as well. I'm just going to flip on to my next slide. There we go. So the streaming view is okay when you've got real data that's coming in, but I'm also going to show you what it looks like if we were to open a real data set. So let's pretend that we've just downloaded a data set, and Ruskin opens it. And Ruskin opens it, and you can see we've got about 10 different channels here, which are consuming a large amount of space in our axis. And perhaps some of them are not channels that the instrument actually recorded. The instrument records what we call measured channels, but Ruskin is also able to derive additional channels. So derived channels would be things like depth, which is a very simple derivation from pressure, salinity, according to PSS 78, speed of sound using a variety of algorithms, Del Grosso and Wilson is what we're using here, oxygen saturation, density anomaly, and so on. So I'm going to quickly hide all the derived channels to show you just on this instrument what was measured. So we still have quite a lot of data going on. And in fact, I know that in this particular, I think it was a weekend cycle, the only channels of interest, I'm just going to show only temperature, and then I'll just show pressure in this tank. So now we've got Ruskin open and open the data set. We've got temperature and pressure here, and we've got a thumbnail view down at the bottom. This thumbnail view, I can reduce its size, and so you can see that the thumbnail now is showing only 3 pressure spikes, which are shown in more detail here. I can grab the thumbnail and pull it sideways to see a variety of things. I can also zoom in vertically and horizontally. So if I place a data cursor here by clicking, and then I use the plus and the minus horizontal buttons, it will center the cursor and then zoom in horizontally. Ignore those little hazard triangles. They're related to a different glitch at the moment. I can also zoom in vertically, and so that will center the data traces on my center of the screen and then zoom in vertically around them. If I want to make this view a bit bigger, just double click on the tab, and now I can see that. Of course, I can see that if I move the zoom window out of my view. So I'll reset that again. Ruskin also has what are known as annotations, and annotations are characteristics that are understood either by the instrument or added yourself that are not part of the data. So for instance, here is an annotation at the beginning, and it's called a comment. And this is somebody leaving a reference check for a salinity value. You can see 35.1360. And if I click on this, I can go into the editor and change that. These are persisted in the underlying data file so that you can then look at those annotations in any downstream processing tool as well. The instrument, if it is set up for profiling at faster than 1 Hertz, will also automatically detect downcast and upcasts and separate them, group them into profiles, but keep them separate as downcasts and upcasts. And you'll hear me talk about that a little bit when we're looking at RSKtools in a few minutes. The variety of annotations that are in here can be selected, and then you can navigate by them. You can add other annotations yourself. So for instance, if you had a handheld GPS and you wanted to put a GPS annotation in, we could do that, and we could say, we'd like to have that here and store the lat and long inside this, inside the instrument. if the Ruskin mobile was used, for instance, to download the data, you will find that every time the instrument came to the surface, it will be GPS tagged. And so you'll actually have a GPS view and a chart view available, not on this file, but on a file that has that was used with Ruskin mobile. I'm just going to see, I'm consulting my other screen, which with Zoom on two screens. I did talk very quickly. I didn't tell you how to download, but on this Ruskin instrument, there is a grayed out, on the simulated instrument, there is a grayed out download button. What I should perhaps say is that if you are downloading many instruments, maybe you've got a batch of 50 instruments that you want to download one after another, connecting the instrument and pressing download can become tedious after a while. And so under the instruments menu, we have these automatic tasks that are available. And if you turn on auto download, or indeed auto deploy, every time an instrument is connected, the download will be made, the default file name will be used without asking for any interaction, and you will simply have a light on the instrument that is red while it's doing something, and then it goes green at the end, which means it's complete. And that permits you or your PhD student to sit there downloading or reconfiguring 500 solo Ts, as some of our customers are doing, without needing to interact with mouse and keyboard and keep them clean and dry. So little features like that that make mass deployments much easier. RSK files. So these files that you get out, these are actually on disk. They look like a proprietary data format that RBR has made up, and you roll your eyes and think, oh, another proprietary data format. However, that's not the case. They are SQLite files, which is a single file database standard, and most programming languages have support for it. So you can open it natively in Python or R or C++ or Java or what have you, without needing to know anything at all about the data. And you can explore it using a SQLite browser and see that it's really just a database of table structures. The RSKtools toolbox for MATLAB that we have is intended to make that even easier and keep you one level of abstraction above the tables so that you don't have to understand how they relate. However, maybe you want to do neither of those things and you actually want to get them in a CSV or into Excel. Perhaps you're just trying to quickly get something done and you don't have time to fire up. You don't like the Ruskin graphs, but you'd like to fire up something else. So you can always export these into both XLSX format and text format. Now in Excel, you're familiar that there are multiple worksheets. And so we separate the data into multiple worksheets to make it easier to use. One sheet has just the data, just the time series plus all the values. The second has the metadata about the deployment, the sampling period, the date you start, the date you stopped, how many samples there were. Another data sheet would have the events, any of those profile annotations, for instance, or if there was a power interruption, those kinds of things. And so the text file is an exact replica of that, but instead of having multiple sheets, we actually create multiple text files and we put them all in a single zip. So that's why the text file export is a zip file. It's because it's got multiple text files inside. Reading, when you want to read the CSV data, for instance, you don't necessarily want to have to count up how many lines in the header to skip. That's why we put the header in a different file. We also support Ocean Data View and a few other less common formats as well. I think at that point, I'm going to skip over, maybe I'm just going to say one more thing about Ruskin, which is to tell you about where to find the help of various kinds. So release notes are always shown when a new version is available, and you can decide whether you want to upgrade or not. The Ruskin user guides and the RBR instrument guides are kept in here, as is the command reference for the L3 command set, which is a lot of what our OEM customers are using. However, if none of those things scratch your itch, then you really want to make a comment on Ruskin. And when you do so, you can enter your name and email address indicate what the problem is that you've run into or the question that you have. You can attach additional files here like RSK files. And so you could have a question about something that you're seeing in the data. But even if you don't attach your data files, this is very useful because when you hit submit, it sends to us the log files from Ruskin. And so if you've got a problem that you don't understand or some behavior that seems strange, comment in Ruskin is often what is done, is requested by our support team. And under the covers, all it does is send a ticket to support@rbr-global.com. If you'd rather grab those log files and send them to us by email, that's fine. The attachment handling, however, in this will deal with RSK files that are many gigabytes in size because it doesn't send them directly as an email. It's an injection into our trouble ticket system. So very helpful in terms of trying to sort out problems or getting a question answered. With that, I think I'm going to pull out of here and flip back to, so I hope maybe Dan, you can just confirm we should have PowerPoint back on the screen.
Yes, we can see your screen.
Thank you. So what is RSKtools? Let's see if I can get that to go away. There we go. RSKtools is a toolbox written in the MATLAB scripting language, available for free, and all the code is there and not locked away at all. And it provides the access to the so-called RSK data files. As I mentioned, they're a SQLite data format. They're used for many different programs. Might use SQLite under the hood for keeping application settings and data files. Many photo editors, for instance, are using it, that kind of thing. And we use it because it's standards-based, and we like using standards rather than inventing our own, and then really adding features on top that it allows us to add them much more quickly. We're currently at version 3.4.1 of RSKtools, but it's compatible with versions of MATLAB that go back about 7 years. There are no additional MATLAB toolboxes that we depend on, so if you've just got MATLAB core, that's absolutely adequate. We do use TOS 10 and I want to say MTides as well, which are two free toolboxes in the oceanographic community. And RSKtools will tell you, if it can't find them, it will tell you where to find them and where to put them. There are almost 50 functions inside RSKtools, and they can be broken down into these 4 categories. Maybe you might call this 5 categories. So I'm going to talk about the readers and writers, which is to say readers and exporters. The readers on the left-hand side, RSK open. I'm going to show you screenshots and examples of all of these, but broadly speaking, the workflow here is that you start off by assigning to a variable the results of RSK open, which is specified with a file name. That reads only the metadata from the RSK file. It doesn't read any data, so it returns almost quickly, almost instantaneously. But it does tell you how much data there is in there or how many profiles there are. And you can then use one of the subsequent read commands to actually slurp in the data. You might not want to slurp in 5, 8 gigabytes of data at a time. And so most of these readers can read just portions of the data. So the read data command is all based on time. You can say a start time and a stop time. So if you've got data that runs over a year-long deployment, you can slurp it in 1-month chunks at a time for processing. Read profiles is based on the information that the logger has put in, saying this is when the profile started and ended, the upcast and downcast, or downcast and upcast. And you can read them in by profile index. You don't need to know where they exist in time. You can do the same if you've got wave data. You can read it in as the bursts. You can also read in the calibration metadata. The exporters are used at the other end of the process, and those allow us to take RSK structures that are in MATLAB memory and write them out to disk in different formats. So CSV, of course, ODV is the ocean data view that we talked about very briefly in the Ruskin view. RSK to RSK is very interesting. It allows you to take the data structure that's in memory and make an RSK file on disk. So let's say you've truncated your data and applied a bunch of post-processing to it, smoothed it, gotten rid of loops, but you'd like to look at it again in Ruskin. Ruskin reads RSK files, so RSK to RSK is the way to get it back there. Of course, you can also use MATLAB's native data format, which is called MAT or MAT, and that's what RSK to MAT does. In between those two things, you're going to view your data and you're going to process it. So I'll go through a number of the calculators and post-processors that we offer, and then talk about some of the plotting tools that we have. Over in this right-hand side, the other group, yes, we've got the help files at the bottom, and then we've got some miscellaneous bits and pieces. When you grab RSKtools, as you can from the website, it comes with a couple of PDFs inside it. And so you can open those, and there are some quick start demos which really walk you through working with a very simple sample file to get familiar with it. The documentation is inside MATLAB, and so you can use help RSKtools in the MATLAB command window, but you can also look at the RSKtools documentation online, and the URL for all of our documentation is docs.rbr-global.com/ and in this case, the slug is RSKtools. Any comments or certainly bugs, our support team is ready to help with. So walk through a quick example. So let's pretend we've got CTD data. What would we typically do as a post-processing pipeline? And your pipeline might vary. We're going to go through 11 steps here. So the first one is to open the file and read some data in, and you can see that that's certainly going to involve RSK open. It might involve reading profiles, reading data, printing the channels out. We're going to visualize some of that raw data, either using plot profiles or plot data. Add some station metadata. So we might know something about a station name from your cruise, for instance, or we might have some GPS lat long that we want to contribute at this point. If the data file only contains measured values and we'd like to derive some additional channels, then we can do that here. So we could derive sea pressure or depth. Actually, step 8 is somewhat an extension of that as well, deriving salinity or potential temperature, theta, or sigma density. Smoothing, aligning temperature and conductivity. Of course, that's a fairly necessary step to start treating salinity spiking, and removing the artifacts of the vehicle that you made the measurement from. So if you were winching out from a ship that wasn't fortunate enough to have a heave compensated winch, then you'll very often have loops in your data and you want to remove those. Plotting again, or even looking at the images that could be composed, or TS plots. And then finally exporting to some of those data formats we mentioned earlier. So this is really all it looks like in MATLAB. RSK, I'm using a variable called RSK, and the whole design methodology of the toolbox is to assign and reassign to the same variable. And that variable has a fairly developing structure as you go through. So RSK opening that file will simply read in the metadata. As I said earlier, it won't read the data itself. We follow that up with a call to RSK read data, where we pass in the same variable RSK and we get out and overwrite that variable RSK. So we are adding some additional information to that variable as we go here. And in this case, we're simply specifying 2 times, a beginning and an end. You don't need to do that. If you skip T1 and T2, then read data will read the entire thing. You know, there be dragons in MATLAB. Its large memory handling is much better than it used to be 10 years ago. And of course, we've all got much larger amounts of RAM available to us, but it's still often quite useful to deal with small chunks at a time. Reading profiles, as I indicated, instead of selecting by time, we can select by the annotation that is known from the instrument. So if we were to look at this RSK using the MATLAB variable editor, you would see that it's a structure. And immediately after opening, it has 17 fields, which range from structures about, substructures about channels, the schedule, the instrument itself and its serial number, the parameters that might be set, how many profiles there are, that kind of thing. If we were to run RSK print channels on it, all we get is a pretty print version of the same thing. So we can see, yes, this instrument was a concerto with a certain serial number, was sampling at 167 milliseconds per sample, which is 6 hertz, and what the channels were named and the units that they're recorded in. When we read data, we add a substructure called data. So you can see that in this screenshot of the editor here. And that data actually has 2 separate fields. One is the timestamp. So the timestamp is the number of rows according to the number of samples we have, and just 1 column. And then the values is the number of rows. Again, it should be the same as the timestamp, and the number of by the number of channels. So you can see this instrument recording has 7 channels in it. We could have read a subset, or we could have read the whole thing. That would just simply change the number of rows in here. This page says really the same thing. When we look at the RSK channels substructure, you can see there are the short name, the long name, and the units. And that was what that RSK print channels function was showing us in a prettier version a moment ago. When we read profiles, instead of the RSK data having one large contiguous block of data, it becomes multiple blocks. And so each of the array of RSK data then is its individual timestamp and values. But you also see we now have some metadata about the profile to say what its profile number is and is the cast in the downwards or upwards direction. So each profile is repeated twice for each cast. Now, the logger may sometimes mistakenly attribute profiles to data that wasn't a profile at all. And so you can take the same data and slurp it in as a time series and generate the profiles yourself according to a pressure threshold. You can look at the help for more details on this, but this is useful, for instance, if you are soaking the instrument just after deploying, but you don't want each of the little heaves from the ship to be recognized as a profile. And so you could set the pressure threshold to be greater, to say that any turnaround that is of less than 200 dbar is not a profile in my book. I'm doing profiles to 2,000 meters or 1,000 meters, and anything less than 200 is me just fiddling around at the beginning. So ignore those. This is an example of adding station data. So in this example, you can see that there's a key name, a key value pair used in RSK add station data, where we're adding some names to the crews, some stations, and a lat long vector as well. And not only in RSK to CSV, but in all the data format outputs, the exporters, this data is preserved. So this allows you, if you didn't put this into the RSK file in Ruskin, you can add it in MATLAB. Of course, if it was added in Ruskin, you can read it in MATLAB as well. When you've got some time series data in, you can plot it just by saying RSK plot data of the RSK and no other parameters, and you would get a figure with 2 subplots for every, or multiple subplots, one for each channel. But you can also specify which channels you do want to view. So this one, for this example, I just plotted 2 of them. This key value notation is common across RSKtools. We try to make the toolbox as consistent as possible. So you'll see that, for instance, in plot profiles, where we want to say, now I want to plot 3 channels, temperature, salinity, and chlorophyll, and I want to plot 3 profiles, index 1, 5, and 10, and I only want to show the downcast. And you can imagine how you change to upcast or to show profiles 1 to 17 in the standard MATLAB notation using the colon operator. RSK images depends on doing some bin averaging first because we need to grid the data. But what this supplies is a time series by pressure view or by depth view of high density profiles. So not as useful for Argo float data, but much more useful for things like gliders or wire walker data, where you might have profiles that only take minutes or hours rather than days to acquire. And so We bin average the data here to something quite small. I think it's about 10 centimeters per second per bin, and then plotted that. And so we've got a quick plot of salinity over looks like just over a 24-hour period, chlorophyll, and you can, temperature and the chlorophyll max, which you can see showing the diurnal variation. Plotting TS plots against potential temperature and PSS 78 is trivial, and we always give you the handles to the plot. If you're familiar with MATLAB graphics handles, that means that you can customize if you want to change the markers and the color and the time series, the labels, and so on. Other processing options that we're able to do then involve smoothing, where you might want to do a boxcar filter over a certain amount of data. You can do running averages or median filters. You can also add your own filters, of course, into this. The critical alignment of CNT, particularly on instruments where they're not correctly aligned in the first place. And that alignment can be done either using a number of samples or as a fixed amount in time, which would take account of variable rates of descent. We've had a couple of other talks about that, and in the YouTube recording of this, you'll see those links to the PDF slides on conductivity, time misalignment, and then dynamic corrections for thermal mass. In terms of, we talked briefly about ship heave and what happens when you don't have a heave compensated winch. Obviously, instead of getting a plot like that, you get a plot that looks something like this scribble. And so you need to remove the data where you've got a loop. And loop behavior occurs in this kind of way. It's where the ship is heaving up and then down again. And so instead of getting a monotonically increasing pressure signal, you get something where you want to get rid of the data where the velocity is less than a certain threshold and where the pressure is not monotonic and you're getting double values. So that's what remove loops does for you. And you can see, whoopsie daisy, you can see that you can specify a threshold for those reversals, and you'll get a diagnostic plot that shows you with these little red dots what it's going to remove out of that data file, out of that data sequence. You can also specify how it should be removed. So it might be in the customary MATLAB fashion to replace those data plot points with a nan and not a number symbol. That results in the lines not being connected when you plot them. You can also replace them with interpolated values if you wish. Despiking is the same kind of thing, looking at low pass filtering and then replacing those spikes. Again, they can be done with nans or interpolated values. And you can have these diagnostic plots if you wish to show what's actually happened. Now the bin averaging, I kind of jumped ahead to, because I said you needed it for RSK images. You can actually bin by anything you like in RSKtools. So you can bin by time, which is the same as doing a block window averaging. You can also bin by pressure, which is very common in any kind of profiling application. So here's an example where we are bin averaging only the downcasts, binning by depth, saying that we want bin sizes of 1 dbar, and we want to start doing it at 1 dbar from the surface. And this behavior is very similar to the way the instrument will do binning itself when it's in the regimes mode that is used most commonly in Argo floats, where you might have, you want to have different regimes throughout the water column. I mentioned that the diagnostic plots can sometimes be shown or turned off, and so this is the visualize true and false that's done here. And that can be done for most of the post-processing functions. The derivation of additional channels can also be done. So you might only have measured oxygen saturation, but you'd like to derive concentration or vice versa. And we'll use the TOS10 toolbox when it's there. I believe we also support the classical seawater toolbox to do PSS 78 salinity. There are a couple more functions, but I'm not going to dive into them now, except to slowly go through them so that they're on the slides and you can look at them in more detail for correcting thermal mass, using both FOSDAR for sharpening and then Lewick and Piccolo to do the correcting of thermal mass. These are some examples on oxygen, and this is the Lewick and Piccolo for salinity correction using the classical alpha beta or alpha tau values. And then finally, exporting. So we can export just a series of channels and not all of them, but you can also export the complete data set, and you will get a CSV that has a header. Ocean data view is very similar. You can also generate RSK files themselves. And so what's interesting is, of course, you can truncate your data and regenerate an RSK, but you could start from any data you have from any other source or instrument. So let's say you've got a barometric time series from a weather station that you happen to have. You can create that or add that to any RSK structure and write it out to disk so that you can then view it again in Ruskin going forwards. And there's a little snippet of code example of how to do that. We develop all this code in Bitbucket in a Git repository, and you're welcome to pull from that directly. If you'd rather just take the released versions, then you can get them, as I mentioned at the beginning, from the data set. And we are then into where to find the manuals, as I mentioned, docs, rbr-global / RSKtools. Or using the help function inside MATLAB. And I think that about wraps it up. Thank you very much for your time. And if there are any questions, I'd be happy to take them.
Thanks, Greg. We had a question from Piero in Virginia with regards to Linux as an operating platform for Ruskin.
So it's a good question. You're not too old school, Piero. I've got to say that I think probably every year the articles are out saying, is this the year that Linux makes it on the desktop? We use Linux a lot, but we do use it on the server side rather than the desktop side. And I think many people who are after the power of a Unix desktop these days tend to be using Mac OS. Ruskin is written in Java, so in theory, it runs anywhere. The other way of making fun of Java is to say write once, debug everywhere. And certainly when we've tried to just quickly spin it up on Linux, we find problems with the JREs and that a wide number of distributions that all do things slightly differently that mean that we can't support it. So we don't have a release of Ruskin for Linux at the moment, but if you put in a vote, we'll add it to it's, to be honest, a very small vote counter, but occasionally we do get people who ask.
Great, thanks Piero for that question. Is there anything else from the audience today? You're welcome to unmute yourselves and ask directly.
Or chat if you like to be a pseudo-anonymous, semi-anonymous. Looks like a quiet one today, then.
Quiet group. I've got a couple questions, just taking us back to the basic interface of Ruskin.
Mm-hmm.
Are there any, within that interface, are there any advanced configurations available for customers who want to change either burst sampling on a wave logger or other things that if they're not totally satisfied with the standard drop-down menus that are available?
I love getting questions from people who know the answers and are just helping me to remember to say something I should have said earlier. So thanks for that. And yes, there are indeed. So under the preferences that I recommended looking at for derived channels, the preferences are also there for advanced sampling controls. And so if you really want to set, for instance, even an end time, where Ruskin typically just calculates it and lets the instrument run out, then you can do that by enabling advanced sampling controls. And there are a number of other things that can be enabled inside there.
Okay. Ian has a question about Microsoft.
I see that. So we don't run, we have Slack here, Ian, and we don't have a outward facing one. You can write into us using a form on the webpage, or email, or the comment on Ruskin functionality inside Ruskin, and we will get back to you as soon as we're online. And that includes, we have RBR staff in multiple different time zones, not just North America, but we cover almost 24 hours of the day between our offices in different countries. So the support is fairly rapid, but we don't have a chat-based solution.
Thanks, Ian, for that. One final question, a really simple one. When you talked about the autonomy engine and the counter that's on the Ruskin software, what happens to an instrument when either the memory runs out or a battery dies? And what can we do to recover our data and get it?
So there's nothing you need to do to recover data. The data is always stored safely regardless of what happens to the instrument. So if a shark comes along and bites your instrument in half, providing you recover the half that has the memory chip on it, the data was safely stored in that memory chip. And in the event of those catastrophic problems, we can actually take the memory chip and perform a little bit of brain surgery, implant the memory into another brain. And when you've got an important deployment, we know that data is worth far more than the instrument's dollar value. And so we will do our very best to recover that data for you. In a less severe failure, like the battery is running out or simply the memory being full, when the memory is full, then we stop recording. But if we are streaming data at the time, we'll carry on streaming data. We just can't record anymore. If the battery runs out, we stop when the battery fails, but we will start again as soon as the battery recovers. And as you know, sometimes batteries have a temperature-dependent failure. So they will fail at a cold temperature, but when the water warms up, the instrument, the battery recovers a little bit of juice, available juice. And so we will start recording again. The same would happen, for instance, although the battery is mounted on some very stiff springs that keep it good electrical contacts. If you hit it particularly hard, you can get the battery to come off one of those springs. But those kind of glitches that might occur, you know, we have people who tow the instruments behind a rib at 30 knots, for instance, in high vibration environments. Those battery glitches are also recovered from automatically. So you might see a time sequence of, I lost my battery, I recovered my battery, I lost my battery, recovered my battery, but you will get data in between them.
Thanks for that. I think our final question comes from Pedro, and I haven't read it to completion yet.
I see that. So Pedro, if you're having problems connecting with Ruskin Mobile on Concerto, then please contact our support team. They do have a way of getting, I think it's some diagnostic files from the iOS device. But even if you just tell us the serial number and the version of Ruskin in your email, that would be helpful because we can just check whether there's any known issues with particular generations.
Thank you, Pedro. I think we're at the top of the hour again. So okay. Greg, thank you for your time today and your expertise. And thanks to everybody for joining RBR for this hour of discussion on Ruskin software.
Thanks for coming. You're welcome, Eloise. Cheers, Piero. Thanks for coming, Veronica.